Hello everybody, it's Mr. Mutson back with Unit 6 Similar Figures. This is Concept 4, 6.4, Parallel Lines and Proportional Parts. This is my favorite section because we get to look at real world problems. And a shout out to Simon, my second period, who loves Gouda cheese. So put me on pause and take a good look at this cheese. Alright, let's move on.
All right, so we did our vocabulary for this unit, very first unit, or section 6.1. So go back and if you haven't done 6.1, go back and do the vocabulary, copy it from here. Let's move on. This is a really cool theorem that we got here. It says basically, if you look at our I-can statement, it says I can use the triangle proportionality theorem. This is also known as the side splitter theorem, like a lot of the jokes that Simon tells in class, to solve for missing parts of triangles with a side parallel to another triangle. So take a look. I've got a proportion sitting down at the bottom there, and it's based that proportion is allowed to be written because DE and BC are parallel. If that's the case, if I have two triangles like that, then I can write proportions between the smaller sides. Now we've already talked about something similar to this where we could break it out into two smaller triangles, or a smaller triangle and a big triangle, and we could write a proportion between say this side, and then this side and this side. Okay, we could write a proportion between those four things. But what this new theorem says is that I can just look at the pieces, the individual pieces, and write ratios between them. Okay, and it makes it much faster for us to get these problems done. So let's look at a couple examples to make sure you know what we're talking about. So as we have talked about in previous class, these two triangles are similar. Once I broke them up, I could look at parallel lines creating some corresponding angles that are congruent, and the two triangles end up being uh, um, similar because of the angle similarity. Because the two triangles are similar, we can say that their sides are proportional. So I could write 12 is to x plus 13, which if you look at the main drawing, that's basically x plus 1 plus 12. And then I could go 9 over x plus 9. That's how we've been doing it up to this point, but there's a shortcut and an easier way to do this. So let's take a look at that real quick in blue. And there you have it. 12 is to x plus 1 as 9 is to x. So that side splitter theorem shows that when I have parallel lines like this, it cuts the sides into proportional parts. So I don't have to add anything together. We're going to take that basic idea and look at a problem like this where we have a bunch of parallel lines and transversals, and it basically cuts pieces up. So what ends up happening in blue here, I can write proportions between pieces that would be equal to their counterparts on the other side. And that allows me to solve for x. So I'm going to put it on pause here, and then I'm going to ask you to go and see if you can write an equation to find z. All right, so there's my proportion. 10 is to z, as 15 is to 12. Now, I could have done 3x plus 5 over z, and so on like that. I could have grabbed a piece a little higher. It doesn't matter, just as long as I grab its partner piece over on the right-hand side. The problem with using 3x plus 5 and z is that now my equation has two unknowns in it, and that's no good. Okay, so there would be an equation that I would use to find z. So let's take a look at some real-world questions. This one's I can use indirect measurements to solve real-world problems. So basically, indirect measurements means kind of these kind of problems. So I'm not going to delve into the details of what indirect measurements is. I just need you to be able to look at a problem like this and see how you're going to write a proportion to solve for the unknown. So it says the surveyor made this sketch from a measurement he made along a river. What is the distance across the river from point A to T? Okay, so we're looking for this distance over here. So go ahead and put me on pause and see if you can think of a way of writing proportion. I would also ask you to, could you, if you're going to write the proportion, is it fair to first of all develop the idea, are the two triangles similar? So put me on pause, think about how the triangles are similar, then see if you can write proportions for it. Okay, as you can tell by my marks, in red, the vertical angles are congruent. We have the right angles congruent. So in each triangle, I have two angles that are congruent. Therefore, by angle-angle similarity, the triangles are similar. And so then I'm going to just relate the side across from the double struck angle on the left, x, goes to the double struck, the side across from the double struck angle on the right. So as x goes with 40. I'm going to do the same thing with 120 and 80. Okay? So it'll just be a matter of cross multiplying and solving for it. Let's do another one. And so as we do these, I'm just going to encourage you to write the equations. Don't worry about solving them. At this point, I'm hoping that you can cross multiply and do all that work on your own. So let's take a look at this one. Go ahead and see if you can figure out what it is they're asking you to do. And then see if you can determine if the triangles, the two triangles, hopefully you see those, that they're similar. And if so, then go ahead and see if you can write proportions to find out what it is that they're trying to ask you to find. All right, so as you can see, first of all, the two triangles are similar. First of all, hopefully the man is upright. He's standing straight up and down. He creates a right angle. The right hand triangle, the tree is upright. It creates a right triangle. And then it says in the yellow there that his eyes, the angle between his eyes and the ground and the tree and the ground, all that stuff is congruent. So again, by angle-angle similarity, I have two triangles that are similar. Now I can write some proportions. So if you haven't done that yet, go ahead and put me on pause and see if you can write your proportions. Don't just watch me do it. Go and do it on your own and think through it, Sima. Okay, so then I have 6 is to 36. The height of the man to the height of the tree is equal to 4.5, the distance he is from the mirror as the tree is from the mirror. Okay, now give me the y. Let's move on to another one. Okay, again, put me on pause, see if you can think through this one. Are the triangles similar? Hopefully you can see the two triangles. Again, this X right here represents the height of the tree. Okay, so we're looking at that there. If you see the two triangles, see if you can determine if the triangles would be similar, and if so, then it allows you to write some proportions. Put me on pause. All right, so I broke it up into two triangles. Take a look at the yellow highlight. The yellow highlight is showing where in the two triangles that I separated, those two angles are exactly the same because, well, they're the same angle. If you look up here, they're coming from the same place, right? So those two angles are congruent, and that's by the reflexive property. All right, so from that, I determined that the two triangles are similar by angle similarity, and so now I'm given permission to write some proportions. Hopefully you can completely see how I do that. Okay, so that's a proportion I wrote. You probably didn't write that proportion, so what I want to do is just give you a challenge here. I wrote that proportion. You determine, is my proportion, your proportion the same one? Might look different, but remember in class we talked about that. Okay? Let's move. All right, so here we have a problem drawn out and everything. I'm going to take the words and put it into the drawing, so I'm going to encourage you to do that same. Put me on pause, draw the picture, put the words, the information from the words into the drawing. All right, let's write a proportion. All right, there you have it. So just again, cross multiply and find out what x is. All right, so I have some special segments I wanted you to look at, and they just create some proportional pieces. It's really straightforward. It's exactly what you'd want to have happen in these drawings, okay? So suppose I have two triangles where the altitudes are drawn. As soon as you have the altitudes drawn like that, their individual parts become proportional. Okay, so if you take a look at the information there, this piece here relates to that piece there. In yellow in the left-hand drawing, that piece, the altitude relates to that piece. So if I was just to simply start writing proportions, relating, writing a relationship, a ratio between two corresponding parts, they should equal the ratio between any two other corresponding. So here's a big test. What do you think is the side that would go with that one? Hopefully you would recognize it would be that one, right? This is really easy. And then how about this piece? Which piece would go with that one? Yep, that long one there. Okay, so with that same philosophy, we're going to look at some other special segments and see if you can just come up with the relationships. Here's an angle bisector, and so see if you can understand how these ratios between pieces should always equal the same things. Let's move on to another one. So you should probably put me on pause each time, write these into your notes and hold on to them so you have them to reference. And then finally, the medians. The medians are coming from an angle and to a midpoint. As you can see, it cuts the segments into two congruent parts. And when that happens, then the triangles also are proportional. Make sure you understand how these parts right here make sense. All right, and there you have it. We have our try it problems. We have two problems to do. If you can't do two problems, I'm not sure what your plan is. There's two pretty basic questions. If you have any struggle with these, come and see me before they're due next class. All right, see you guys next time.